Okay, so the plan for today is to continue with 7.1, multiplying and dividing rational expressions, finish up a couple of problems there, and then move on to 7.2, adding and subtracting rational expressions. Um, Remember that the Unit 2 exam is this week. It does seem like the password screen on exam or on WebAssign is working, um, so I think that was just a glitch with that one exam and that one course from a couple weeks ago, and everything should be working well now. The exam is currently available. It'll be available through this coming Sunday the 3rd at 11:59 p.m. But I recommend that you plan on taking the exam probably Thursday evening or Friday morning at the latest. The material in the exam is chapters 4 through 6, and there's a sample exam posted that should give you a pretty good idea of what's on the exam. You can use a calculator as long as it's only a calculator, so no tablets or phones or smartwatches, anything like that. Scratch paper and pen pencil on the exam. So take a look at the announcement for more information on that. Um, and then the quote of the day for today, there's two quotes. One is from the philosopher Friedrich Nietzsche. He wrote in German, so there are several different translations of this, but I think this is a pretty good one. Um, Whoever fights monsters should see to it that in the process he does not become a monster. And if you gaze long enough into the abyss will gaze back into you. And then I think hitting at the same theme from the Silmarillion, the world building book for the Lord of the Rings series, The Hobbit, Lord of the Rings, etc. Um, for those who defend authority against rebellion must not themselves rebel. So it's easy to, you know, on principle, fight back against a certain idea or fight back against something, but then the fight kind of allow the fight to kind of become its own principle and lose track of the original goal. So maybe some caution against that. Okay, so I think that was all that I had to say about the exam, and let's move on to rational expressions. So section 7.1, multiplying and dividing rational expressions. We talked last time about what is a rational expression. We talked about restricted values, and we did some simplification and multiplication. Now let's talk about dividing rational expressions. So if we have the ratio of two rational expressions, let me actually try to bump this down to the next line. There we go. If you put it on its own line, it's zooms in a little bit so you can see it a little better. So we have two rational expressions here, r squared minus 9 over 15 and r cubed minus 27 over 5r squared plus 15r plus 45. And we want to divide these rational expressions. So we actually have kind of three ways to get restricted values here. One place that gives rise to restricted values is the denominator here. Sorry. So in this first fraction, in this first rational expression, the denominator can't be 0. Now, in this case, it's just the number 15, so we don't pick up any restricted values there, but if we had something more complicated, we could have some restricted values coming from there. In our second rational expression, we have a denominator as well. This one probably will give rise to some restricted values. But the third thing that we have to be careful about is we note that we have a division here. So we actually have a third way to get more restricted values, and that's when this entire rational expression, the second one, the divisor, is 0. So checking for restricted values is going to be somewhat non-trivial here. We check when is the first denominator 0, when is the second 0, and then we ask when is the divisor rational expression, the second rational expression here, when is that entire thing 0? Well, a fraction is 0 when its numerator is 0. So this is really just equivalent to r cubed minus 27 equals 0. So we really have three different places to get rational expression, or to get restricted values from our rational expressions. Of course, 15 is never 0. So we get no restricted values here. The second equation, the denominator of the divisor being 0, well, we have a greatest common factor of 5 that we can factor out. And I need to figure out when is r squared plus 3r plus 9 equals 0. And what do I get here? I end up with, well, I'm looking to factor 9 into a product of two numbers that adds to 3. I don't see a nice factorization here. So I'm going to kind of put a question mark here. This is going to be a type of quadratic equation that we can't solve with the techniques we've used so far. So a little side note, this problem in the book, I don't think the book always wants you to explicitly write out the restricted values. I think it's a good idea to do. We've already had a little bit of a discussion about this. I call restricted values something a little different than the book does, and I think it's important to state what they are every time. But I grabbed this problem from the book and thought it was just a good example of how we need to build up maybe a few more tools or techniques to really be able to answer all of these problems uh, that could come up in even a problem like this one. So for this one, let's say to be continued. So we'll see whenever we get into a deeper study of quadratic equations, quadratic formula, and so on, we'll then be able to solve this kind of an equation. And then r cubed minus 27 equals 0. Well, that says that r cubed equals 27, or r equals 3. So I have one restricted value, r cannot be equal to 3. If r was 3, then this entire second rational expression here would be 0. And I would have something divided by 0. So I'll come over here and just say r cannot be equal to 3. And we'll forget about this one for the time being. Okay, so now I want to go through the process of dividing and simplifying. If I have fraction divided by fraction, if it was, say, 2/3 divided by 4/9, what would I do? I would invert and multiply, or I'd multiply by the reciprocal and make this 2/3 times 9/4, and then start dividing out common factors. Well, I'll do the same here. The process isn't any different just because my numerator and denominator are rational expressions. The process is the same. So I have r squared minus 9 over 15. I leave my first fraction the same. And then I multiply by the reciprocal. And now I want to factor things out. I know that when I multiply fractions together, I multiply the numerators, I multiply the denominators. I know that r squared minus 9 factors into r plus 3 times r minus 3. I can factor a factor of 5 out of this numerator in the second fraction. And then I'm left with r squared plus 3r plus 9 divided by 15 factors into 5 times 3. So I can get a prime factorization for that. And r cubed minus 27, I know that I'm going to get an r minus 3 out of here. This is r cubed minus 3 cubed. And I'm going to be left with an r squared. I need to make a minus 27, so that's going to be a plus 9. And then I have a cross term that's going to help with some cancellation, help things cancel out. So let's figure out what I have here. I have r times r squared is r cubed. I have plus 9r. And then I have minus 3r squared and minus 27. I want to keep the r cubed in the minus 27 terms and get rid of the r and the r squared terms. So I need r to multiply by something and give me a minus 3r squared. That's going to be a minus 3r. And then when minus 3 multiplies by minus 3r, that gives me, I need the opposite of that. I need to get rid of the minus 3r squared. So r needs to multiply plus 3r to get plus 3r squared. And then when the minus 3 multiplies by the plus 3r, I get minus 9r. And these go away. So you could either memorize the sum and difference of two cubes formula, or you could kind of build it when needed. Okay, and I see that nicely enough, these divide out. I see that these divide out, and the 5s divide out, and I'm left with just r plus 3, all divided by 3, with the domain restriction r not equal to 3. Any questions so far? And kind of as an aside, we see that r cubed minus 27 factored to something with this as a factor. So we can infer from the work that we did that there are no solutions to this equation. There are going to be no more restricted values because r cubed minus 27 only has r equals 3 as a solution. It would have to have more solutions for r squared plus 3r plus 9 to be equal to 0. But we'll see that a little more explicitly and a little more readily in future sections. Okay, and then this example of divide and simplify. So let me again bump this down to the next line and make it a little bigger, easier to see. So here I have a rational expression, 2x squared minus 10x minus 48 over 2x minus 1. So I have a rational expression that's being divided by, well, this is just a polynomial, but a polynomial is basically like a rational expression, right? I could always take this polynomial here and say, put it over 1 like that, and it looks a little more like a rational expression now. Did I erase one too many? There we go. And so I see that I have 2x squared minus 10x minus 48 over 2x minus 1 divided by 4x squared minus 32x over 1. And again, just like above, there are 3 ways here that I could get a restricted value. When this is 0, when this is 0, or when this entire second rational expression is 0. So let's look for restricted values. Well, when is 2x minus 1 equal to 0? When is the other denominator of 1 equals 0? And when is the entire second rational expression 4x squared minus 32x over 1 equals 0. Well, 1 equals 0, of course, no solutions there. 2x minus 1 equals 0, though. X equals 1/2. That's a restricted value. And 4x squared minus 32x, I can factor a greatest common factor out of there of 4x times x minus 8. And I see this has solutions x equals 0 or x equals 8. I actually have 3 restricted values here, 2 of which came from this entire second polynomial or rational expression being 0. Now let's go through the operations, through the division, factoring, simplification. And instead of dividing by this second fraction, I want to multiply by its reciprocal. So let me multiply across the top, multiply across the bottom, factor everything out, and see what divides out. I note that 2x squared minus 10x minus 48 does have a greatest common factor of 2. And I can factor that same 4x out over here, leave me with x minus 8. And then lastly, I can factor my numerator. Here I'm looking for 2 numbers that multiply to negative 24, so they should be opposite in sign, and then add to negative 5. I think something like 8 and 3 are going to do the trick. So maybe negative 8 and positive 3 multiply to negative 24 and add to negative 5. And as a little aside, kind of a test taking strategy is if you have one of these problems pop up on a test, you know, chances are pretty good that you're going to want to do some simplification, right? If somebody's chosen the problem to be, say, in a textbook or on WebAssign, or if I chose the problem for an exam, there's a pretty decent chance that when you invert and multiply, something's going to cancel out. So that can even help you a little bit in your factorization, right? You're looking for a 2x minus 1 or an x minus 8 to come out of this factorization. That might give you a hint where you might want to look. Now, of course, we don't want to just assume that, say, 2x minus 1 is a factor and run with it. But if we wanted a little bit of a hint of what m or n might be, and we might be looking at negative 8 as a possibility for one of them because we see that x minus 8 in the denominator. Yeah, and we're anticipating that something's probably going to cancel out. And indeed, the x minus 8 factors divide out. The 2 divides with the factor of 4, leaving a 2 on the bottom. So this gives me x plus 3 divided by 2x times 2x minus 1. And again, with the domain restriction of x cannot be 0, 1/2, or 8. And I think that's about as simple as we can get it. I probably wouldn't go through the trouble of multiplying the denominator back out. At this point, it's I think personal preference whether you consider this simpler or multiplying the denominator out. But certainly we would want to divide out these factors. So we want to make sure we divide out all the factors, and the form that we get, we can call this the simplest form. Okay, and then looking at rational functions, well, we've kind of seen that, thinking of something as a function is not too much different from just working with expressions. So here I have r of x equals p of x over q of x. We're going to state the natural domain of R and simplify the rational function. So we're using different terminology, but we're basically going to do the same process as above. So here I have a ratio of two polynomials. I have a problem. I have a domain restriction whenever q is 0. Or that is whenever x squared minus 4 is 0. Or when x plus 2 times x minus 2 is 0, or when x is plus or minus 2. These are restricted values for a rational expression, or these are domain restrictions for a rational function. So we might say something like domain is, I might say like all real numbers take away the set 2 and -2. Or I guess I could say it in interval notation, minus infinity to minus 2, union minus 2 to 2, union 2 to infinity, all open intervals. So we're excluding -2 and 2. I could kind of say it either way. Or I could just write out all real numbers except 2 and -2 if I didn't want to remember all these symbols. Okay, so then what is R of x? Well, it's p of x, x cubed plus 3x squared minus 4x minus 12 over q of x, x squared minus 4. And under this domain, we're going to do all these calculations. We've already said what the domain is, so we don't have to, rewrite it again. We've already said what the domain of R is. The numerator, I see it has 4 terms. It's a cubic. Pretty much my only hope of factoring this is factoring by grouping. So let's see if that works. From these first 2 terms, I can factor out a common factor of x squared, leave me with x plus 3. And then can I get an x plus 3 left over for my second 2 terms? Well, yeah, if I factor out a -4, that leaves me with a factor of x plus 3. And in my denominator, I actually see that this is going to shape up nicely. So I'm not going to even factor my denominator, because I noticed that when I factor x plus 3 out of the numerator, I'm going to get exactly x squared minus 4 as one of my factors. So these whole x squared minus 4 factors divide out. I didn't have to factor them into x plus 2, x minus 2, although if I did, it wouldn't have been a big deal. I would have just had the x plus 2's divide out and the x minus 2's. But this all leaves me with just x plus 3. Now it is important that I remember my domain restrictions, that I can't plug into a -2, because I lost the implication of that here. If I just wrote R of x equals x plus 3, the implied domain would be all real numbers. But R of x as this ratio, we can't plug in plus or minus 2. So a rational expression function R of x simplifies to x plus 3, but its domain is all real numbers except 2 and -2. So this is going to, what would a graph of this look like? It would look like this, except at 2 and at -2, I guess would be about here. I would have an open dot at those locations instead of a closed dot. So I guess I could clean that up just a tiny bit here. So that is what R of X will look like. Note that if I just had said, hey, I have a rational function R of X equals X, or oh, sorry, I have a function R of X equals X plus 3, we would assume it's natural domain is all real numbers, and we'd have this whole line here filled in. But since our rational function came from the quotient of these two polynomials, we have domain restrictions where Q equals 0, and that gives rise to some holes in our graph. Any questions on 7.1 on what are rational expressions or rational functions, how to multiply them, divide them, or simplify them? Okay, so let's move on to 7.2 then, adding and subtracting rational expressions. So we know rational expressions are basically fractions, and we know that adding and subtracting fractions is a bit more difficult than multiplying or dividing them. So let's take a look at a simpler case first. Here we're adding two rational expressions together that have a common denominator. So I see in my first rational expression, I have a 2x minus 1 in the denominator. Same with my second rational expression. Now, if I think back to fractions, just numerical fractions, if I have something like 1/5 plus 2/5, say, well, my 1/5 represents the 5, represents, say, taking a whole, like a whole pizza or something like that, slicing it into 5 slices. And the numerator represents having one of those slices. 2/5 pretty similarly. I have a pizza, I slice it into 5 slices, and I have 2 of those slices. Well, these are all kind of similar slices. I can just basically pop this into there, kind of fill in one of these, and I see that this is 3/5. So I add across the top. 1 plus 2 equals 3. I have 3 slices because one person had 1 and the other one had 2, and they combined them together. So I have 3 total slices, and the slice size is 1/5. So I add across the top, but I keep the denominator the same. I don't add across the denominators too. I don't like add 5 plus 5 equals 10 or something like that. Because the 5 in the denominator is telling me it's telling me how big my slices are, or how many slices are in each whole pizza. So just combining, these slices together didn't change the slice size. I didn't re-slice them up or anything like that. Okay, so adding and subtracting rational expressions works similarly, right? This 2x minus 1, we can think of it just like a number. I mean, it has a variable in it, but it operates basically just like a number. That variable is just a placeholder for a number. So I've taken my whole pizza and I've split it into 2x minus 1 slices. How many of those slices do I have in my possession? I have 2x squared of them. I took another whole pizza and I sliced it into 2x minus 1 slices, the same number of slices. The slice sizes are the same between these two pizzas. How many of those slices do I have? I have 15x minus 8 of them. If I want to add these together, I add the numerators. keep the denominator the same. I don't want to add the denominators or do anything like that. I'm just combining slices together. If you bought, two medium pizzas from Domino's and they had 8 slices each, if you ate some of the first and some of the second and put the two pieces together and this pizzas together in the same box, you didn't change the size of the slices. You just combined together some slices. Okay. I want to do two things here. Number one, I want to keep in mind my restricted values. Well, the only place that I have a denominator here is this 2x minus 1. I'm adding two rational expressions together, so I don't have to worry about whether one whole rational expression is 0 or not, like I did whenever I was dividing them. And I have the same denominator in both rational expressions. So 2x minus 1 is the only place that I'm going to be looking for restricted values, or x equals 1/2 would be a restricted value. So x cannot be 1/2. And now I want to simplify. I want to factor the numerator and see if anything divides out. The 2x minus 1 doesn't factor. Nothing, not even a greatest common factor comes out of there. In my numerator, again, if I can certainly factor this from first principles, but if I use a bit of a test-taking strategy here, I think that, the only interesting result from factoring the numerator would be if I get a 2x minus 1 factor, because then I could divide that out with the denominator. If 2x minus 1 is a factor of 2x squared plus 15x minus 8, what would the other factor have to be? Well, 2x would have to hit something to make 2x squared. That would have to be an x. -1 would have to multiply by something to make -8. That would have to be a +8. Now, I'm not sure yet whether this is right. This would make my quadratic term and my constant term right. I have to check the middle term. My outer and inner combine to give me the middle term. My outer gives me plus 16x. My inner minus 1x. That does give me plus 15x. Right, so this made the factoring process a bit easier because I made an educated guess. I can divide out my 2x minus 1s, and I get x plus 8 with the domain restriction, x not equal to 1/2. So if I have a common denominator, I just add the numerators, keep the same denominator, find my restricted values, factor and simplify. Okay, now I have something that looks a bit more complicated. Subtract and simplify for these two rational expressions. Each of these has a quadratic in the numerator and the denominator, but again, I recognize that the denominator is the same between the two of them. It's a little more complicated than before, but it's the same thing. I mean, it's the same as in these two denominators are the same thing. So what do? Well, I subtract across the top. And I keep the same denominator. Subtracting across the top gives me 6x squared minus 5x squared is 1x squared. 3x minus x is 2x. And 4 minus 7 is -3. Now I want to look for restricted values. So I want to know, Are there any real solutions to x squared plus 4x minus 5 equals 0? So I'm looking for what? Two numbers that multiply to -5 that add to plus 4. I think that is plus 5 and minus 1. Right? They multiply to give me -5 and they add to give me positive 4. So x equals -5 or positive 1 are restricted values. Let me factor the numerator, factor the denominator. Well, I've already factored the denominator, but factor them both, divide out any common factors. So I have x plus 5 times x minus 1 on the bottom. And I'm looking for two numbers for the numerator that multiply to -3, add to positive 2. I think that is x plus 3, x minus 1. 3 and -1 multiply to -3 and add to positive 2. And I see the x minus 1s divide out. So I still do see the implied domain restriction x plus 5 coming from x plus 5, that x cannot be -5, but I've lost the implication that x cannot be 1. So I have to make sure to have that in there explicitly, that domain restriction. Any questions so far? Okay, let's look at this next problem. X squared plus 3x over x squared minus 9, subtract 3x minus 27 over 9 minus x squared. Now I look at this and I see that, again, I have a difference of two rational expressions. It would be nice if they had the same denominator. These ones don't have the same denominator, but it's really close. One denominator is just the opposite of the other, right? X squared minus 9 is just -1 times 9 minus x squared. One of my denominators is really close to the other one, but not quite exact. But I could pretty easily make this a problem with common denominators. This minus here I can think of as plus -1 times my rational expression. But remember a fraction property, I'll kind of write it over here off to the side, that if I have, say, -a over b, that's the same as -1 times a over b, but that's the same as -a all divided by b, or a all divided by -b. So if I have like a -1 factor in front of a fraction, I can kind of attach that negative to the entire fraction, or just to the numerator, or just to the denominator. So what does that mean? Well, I can write plus 3x minus 27. I'm not attaching that negative to the whole fraction or to the numerator, but I'll attach it to the denominator. In other words, I get -1 times 9 minus x squared, or that's x squared minus 9. If my denominators are only different from one another by basically just a constant, just a numerical factor, it's pretty easy to force one to look like the other one. So here I just use this minus here from the subtraction to effectively flip the order of these terms and make my two denominators look alike. And now I pretty clearly see that I get x squared plus, well, plus 3x is plus 6x minus 27 divided by x squared minus 9. When is my denominator 0? When x squared minus 9 is 0, or when x plus 3 times x minus 3 is 0. X cannot be plus or minus 3. And now I will factor, divide out common factors, and get my answer. So my denominator is simple to factor. X plus 3 times x minus 3. My numerator a little more complicated, looking for two numbers, m and n, such that their product is negative 27, so they have to be opposite in sign. And their sum is 6. 9 times 3 is 27. 9 times negative 3 is negative 27, and 9 plus negative 3 is 6. So I think this is going to be x plus 9 times x minus 3. I see my x minus 3's divide out. And that's my answer. So one little word of caution here. It's a little bit easy to see the big picture and get lost in the details, or vice versa. It's easy to, to be proficient at the details and get lost in the big picture. But I think particularly in something like this, it's easy to look at something like x plus 9 over x plus 3 and try to do something like divide out the x's and make it 9/3 or 3. Or to say, divide the 3 into the 9 and leave me with x plus 3 over x or something like that. Right? These are not valid operations. When we're dividing out between a numerator and denominator, we need to have a factor times the entire rest of the numerator. Right? We have a over b equals a times c over b times c. So if I wanted to divide out my c's to simplify to an a over b, I need to have c times everything else in the numerator and c times everything else in the denominator before I can divide out. I just need to be really careful with applying my rules from basic arithmetic carefully and systematically and precisely to this more complicated scenario. So I can divide out an x minus 3 here because I have x minus 3 times the entire rest of the numerator. And similarly, x minus 3 times the entire rest of the denominator. But I would not want to say try to divide out these x's because those x's are added on to the numerator or the denominator. So we want to keep straight, our division is in this level of PEMDAS, but addition subtraction, like in x plus 9 or x plus 3, is in a different level. So they don't mesh so well together. X plus 9 over x plus 3, even though it might look at a glance like there's some more stuff maybe we can cancel out, there's really nothing we can cancel out here. Anything that we would want to cancel out, like the x's that kind of look the same, they're added or subtracted onto their respective numerator or denominator. But the overall operation is division. Those two operations don't mesh. They're not on the same level of order of operations. Any questions? Okay, let's look at this next one. So now we're looking at, again, like kind of one more step up. Here we have rational expressions where the denominators are monomials. where we only have one term in each of the denominators. And I can see with a monomial, it's not too difficult to manufacture a situation where I have a common denominator. If I look at 10x squared y and 15xy squared, I would like to find a lowest common denominator. Let's forget about the x's and y's for now. Let's just think if we had like 7/10 plus 4/15, what would we do? So let's come over here. Well, if I wanted to find an LCD for this, I would take 10 and 15. I would write each of them in their prime factorization. So 10 is 2 times 5, 15 is 5 times 3. And the lowest common denominator is the least common multiple of the denominators. So I need a 2, a 5, and a 3 factor in my LCD. The way I like to think of this is kind of like Lego building blocks. Like I want to be able to build a 10, and I also want to be able to build a 15 from my Lego set. And not necessarily at the same time, right? I can use some Legos to build a 10, take them apart, and then use some others to build a 15. So what do I need to have in my Lego set? I need one block of 2, one block of 5, and one block of 3 to build a 10 or a 15. So this would be 30, right? And then I would convert each of these fractions into an equivalent fraction with a denominator of 30. So I'd have 7 times 3 over 10 times 3, 4 times 2 over 15 times 2. I'm going to do a similar thing here. So 10x squared y, what's its kind of prime factorization? Well, I have one factor of 2, one factor of 5, two factors of x, and one of y. 15, one factor of 5, one factor of 3, one factor of x, two factors of y. So my LCD, my least common multiple of these two expressions, it needs to have a 2 so that I can use that 2 if I need to build the 10. It needs to have one factor of 5, which will be used in either the 10 or the 15. It needs to have one factor of 3 in case I need to build a 15. For the x's, well, if I only had one factor of x, I could only potentially build a 15xy squared. I could not build the 10x squared y. I wouldn't have enough factors of x. I need two factors of x. I need the highest power. And then same thing with y. I need two factors of y. If I only had one factor of y, I could only build the 10x squared y potentially, but not the 15xy squared. I wouldn't have enough factors of y to build the 15xy squared, so I need two factors of y. So my lowest common denominator is 30 x squared y squared. Now I look at my first fraction, 7 over 10x squared y. I want to multiply 10x squared y by something to make 30x squared y squared. Or in other words, I want to just figure out what is missing in this 10x squared y. Kind of if I build a 10x squared y, what Lego bricks do I have left over? Well, I would have a factor of 3. 3 times 10 gives me 30. I don't need any more x's because I've used both of my x Lego bricks in the 10x squared y, but I have one more factor of y that needs to be put in. And of course, if I multiply by that on the bottom, I need to multiply by it on the top as well. That's my equivalent fractions property. And then my second rational expression, I have 15xy squared. So 15 times what gives me 30, that's 2. X times what gives me x squared, that's x. Y squared times what gives me y squared, that's just 1. There's my 4 over 15xy squared. If I multiply by 2x on the bottom, I've got to multiply by 2x on the top as well, so I don't change the value of the fraction. Now, if I take my first fraction, my denominator is going to be 30x squared y squared. My numerator, 7 times 3 is 21y. And my second fraction denominator, 30x squared y squared, and numerator, 8x. And lastly, I can add these together. 21y plus 8x over 30 x squared y squared. Nothing in that numerator factors. There's no greatest common factor. There's not a numerical greatest common factor or a variable greatest common factor to pull out and try to divide with some of the factors in the 30 or with an x or a y. So at this point, I'm done. I might, for good measure, want to say x cannot be 0 and y cannot be 0, but I actually didn't divide anything out, so that domain restriction is still implied. Wouldn't really be the end of the world if I didn't explicitly say that, because nothing divided out. It's more important whenever something divides out to say what the domain restriction is, like up here, because we can lose that implied domain restriction when we have something cancel out. Any questions on this? Questions on anything that we talked about today so far? All right, I think we'll end a couple minutes early today because this next problem is probably going to take us a bit longer than we have left in class, or at the very least, I have to rush at the end, and I don't want to do that. But next time we'll be looking at adding, subtracting, and simplifying rational expressions with unlike denominators, where it takes where it's not a trivial process to get a like denominator, like just switching the sign or multiplying by a factor here or there, but where we have to go through a bit more complicated process to figure out what's the lowest common denominator, convert everything to a common denominator, and then simplify. So these problems are a bit more involved, a bit more lengthy, which is why I don't think I can comfortably get it done in 5 or 6 minutes. So just a reminder, our exam is this week. I know a couple folks reached out with questions about Examity, and I think I answered everybody. I answered a couple of them just this morning right before class. But I do have office hours today from 12 to 1:30. Probably be, maybe like 12:05 or so. It takes me, sometimes a couple minutes to close things out and answer any questions for my class that ends right at noon, before I turn it around for the office hours. So, around noon to 12:30, or sorry, noon to 1:30 today, or 9 to 10 a.m. tomorrow, I have office hours if you want to pop in and work through any of the Examity stuff. Or if if any clarification wasn't enough, let me know and we can definitely get that worked out. So, but I think overall, Examity is working pretty well, and folks have had not too many tech issues with it. So, so it should be working. And if you're not able to get it up and running, let me know. All right, I will see you all on Thursday then.